All right, continuing on with this shader fiasco, we have the mother pooping pixel shader. So I made pixel shader.hlsl. I set up the settings here. The pixel shader type is pixel shader, output is project directory, and we're ready to roll. Now, pixel shader. Good questions. What does it input? What does it output? Well, the output is easy, right? Think back to 3D fundamentals. Pixel shader is going to set the color of the pixel on the raster. So it's going to output a color. What is a color? Float 4. That's what color is. You might think that doesn't make any sense, Chili. We never use floating point for color. Well, we did, right? In 3D fundamentals, when we wanted to interpolate colors, we used floating point. And that's why Direct3D tends to use floating point for colors in its shaders. Easy interpolation, easy calculation. So, 4-dimensional vector, that's your color. RGB and alpha. We're not using alpha, but hey. Okay, name of the thing is main. It takes 0 parameters. And you might be saying, that's weird. Why does this shader not take any parameters? What about the position of the pixel? But the pixel doesn't need to know its own position on the screen in order to draw itself. Think back to 3D fundamentals. How many of our shaders use the screen position of the pixel? Not very many. The position of that pixel in the world, the actual geometry that it corresponds to, sure. But right now, we're just drawing a flat colored triangle. We don't actually need, it doesn't depend on anything. We're going to output a constant color. So we're not taking any input. The output needs a semantic, SV for system value, and the name of that is target. So that stands for render target because that's what we're going to. That's just what the name they gave the color. I don't know. Doesn't matter. So SV target. Pixel shaders can also output depth, but you don't want to do it that often. There are problems with it. But anyways, we're mostly just going to be outputting color. So here is our shader, and what do you call it? Signature all set up. Output, no inputs. What are we outputting? Well, that is incredibly simple. Glad you asked. Float 4 and just give us our color. So what color do we want? Well, let's give a nice white triangle. So that's 1, 1, 1. The last one doesn't matter. Let's just make it 1 for consistency. And there you go. There's your freaking pixel shader. Are you happy? Are you not amused? Anyways, so we've written our pixel shader. Let's see if it compiles. No problem there. Now we got to do is load that mother trucker. And the code to load and bind the pixel shader is almost identical to that of the vertex shader, so I'm not going to make you sit here and watch me type it all out. Long story short, this is what you get. We're going to create, pointer for our pixel shader. We're going to read into our blob. We're reusing the blob that we used before because we don't need a new blob, right? We're done with that old data that's in the blob, so we'll reuse the blob. We'll load the bytecode, we'll create the pixel shader. Same deal as this one. It's pretty much just mirrored, just replace vertex with pixel, and then we bind that. There you go. Beautiful. Let's build it. And now we get more errors because now we have bound a pixel shader, so now it's going to expect a bunch of new stuff. Indeed, it expects a render target view bound to slot 0. And looking at this diagram again, it makes a whole heck of a bunch of sense because the pixel shader outputs the output merger, which then goes into the render target. But we haven't specified a render target. And they may be saying, well, obviously, Chile, I want to render to the back buffer. Where else am I going to render to? But Direct3D allows us to render to off-screen targets. So you can say render multiple passes onto the same target and then combine results onto a final. You could do things like full screen filters or, I don't know, a whole bunch of other, whatever you want to do. The crux of the issue here is that if you don't specify the output target, Direct3D ain't going to know where to put your pixel shader output. So as usual, anytime we're doing something with the pipeline, probably going to be using the context interface. And we know that the pipeline stage we're working with is the output merger, so that's OM. And then we want to set, and what have we got here? Set blend state? No, set render targets. And we notice here, targets, plural, so we're probably going to need an array of stuff here. So how many views do we want to bind? We want to bind 1. And now we need our render target view. Now, luckily, we've already got that bad boy, right? We created that in order for us to clear the buffer because you need a render target view interface in order to clear your back buffer. So we've already got that guy. We just need now because it takes render targets, it wants an array of pointers, which is a pointer to a pointer. So we can just, an array of 1 is just a pointer to that pointer. So we can go address of p target. And then the last thing we bind is the depth potential view. And we don't have, that's Z buffer. We don't have one of those yet. So we're just going to set that to null putter. And there you go. Now, there's a huge problem here, but let's just try and build it and see what happens. So we get something peculiar here because we're still getting the exact same error. We've set the render target, but it says it expects a render target. But bro, we set that. Well, here's the thing. We actually didn't. We actually screwed up. And those of you who were paying attention during the COM pointer video might have already caught this. But this is very bad. This is no bueno. So what is the problem? Well, we're giving it a pointer to a pointer because it wants a pointer to an array of pointers. And this will do that for us. It'll give us a pointer to the underlying pointer, the pointers that is being held by the smart pointer object here. But this operator has 2 tasks. The first task is to give you the pointer to the pointer. The second task is to free anything that is currently being held. Why is that? Well, because the whole point of this, and the reason, the main usage of it, is getting a pointer to the underlying pointer so that it can be filled by some COM function. However, in this case, we're not filling the pointer. So there is no reason to free anything that is existing. And if we freed it, that would ruin this whole function call. So here, this behavior of the address of this is very nice because this p blob was already holding an interface to the blob returned by this function. But that is going to be released so that it can be filled with the interface returned by this one, which is going to be a different blob. If it didn't have that behavior, this would be a memory leak right here. If I replace this with get address of, that'd be a big old memory leak. So we don't want to free. What do we do? Well, we can call a function get address of, and that will give us the address of the underlying pointer without freeing the interface currently being held, and that is super important. And that's going to fix our problem. And so now you see that error goes away and is replaced by another error that there are no viewports currently bound. But before we get to that, let's address something, the elephant in the room, and that is here we're also setting index buffers. It is also looking for a point, we're looking for PP, but it's looking for PP in all the wrong places. It's looking for PP, the array kind of PP, not the filling kind of PP. So we should replace that with get address of, and now that's going to work properly. Didn't give us any errors, but it would have screwed us over in the future. So let's cover it while we're on the topic. So now we've got that fixed. Let's look back at our error. So it's telling us that there are no viewports, and if you are rasterizing, you need viewports. What's a viewport? Well, the concept is quite similar to the screen transformer, the pube screen transformer that we did in 3D fundamentals. So what it's doing is it's mapping from NDC space. Let's take a point in NDC. So what's the coordinates of this point? Well, it's going to be 0 in the x, and it's going to be +1 in the y, right? What does this map to on screen space? Well, that would map to, assuming that this is mapped to the entire screen, in screen space, in our current dimensions, that would map to 400, because we're 800 by 600, and 0, because y is going down, and the origin is at the top left here. Where here, the origin is at the center, 0, 0. So, that's one thing that the viewport does. It does that mapping for us. But it's not all, because we can actually specify a sub portion of the render target, and that's the viewport, and then it will map our rendering space onto that sub portion. So now this would map to here, which would be 200 0, and that's great. We could use that. We could do like side by side split screen, or top bottom split screen, or we could use the bottom for rendering a HUD, and the top would be rendering our game view, or whatever. It doesn't matter. The point is, you've got some flexibility for viewports, but that means you've got to set up some shizzle. And I'm just going to type that out here real quick like, and that looks something like this. This is simpler than other configurations because we don't have to create a direct 3D object and then bind it to the pipeline. We just create a structure, and we call directly a function on the pipeline to set up the viewports using that structure. So the function we call, it's on the rasterizer stage, set viewports. And you can see here, viewports, so it is going to expect an array of viewports. But we can just give it a pointer to a single viewport, and that'll look like an array of one element. Great. So the viewport structure, very simple. You give it the width and the height of the viewport. You give it the coordinate of the viewport in the render target. So the top left is going to be 0, 0, because we want the entire screen. And you can also specify min depth and max depth for it to map the depth values. But since we are not doing depth yet, we're just rendering a two-dimensional triangle, this doesn't really matter for us. I just set it to 0 and 1. For the time being, we configure the viewport, and if we run this, we should see fewer errors. And indeed, we do have fewer errors. We're down to 2 now. So let's look at this one here. Current primitive topology value 0 is not valid. So apparently we need to set something called a primitive topology. So the $5 million question is, what in the butt is a primitive topology? And well, in 3D fundamentals, our pipeline could render anything as long as it was a triangle list, index triangle list to be specific. Well, in Direct3D, you have got some options on what you can render. Look at this here. You can render points, you can render lines, you can render triangles, and you can render them in list configuration or strip configuration. So you got options, and you got to tell Direct3D which one of these the vertices, because you're just sending it a big list of vertices. It doesn't know whether to interpret them as lines, as triangles, as points. What do we do? How do we do? So let's look at this. Here is a visualization of all the different things. So point list, very simple. Vertex 0 is 0.0, vertex 1 is 0.1. Great. Line list, vertex 0 and 1 give you the first line, vertex 2 and 3 give you the second line. That makes sense, right? Ignore this adjacency, that's to do with geometry shaders. We'll not be covering that for a while. Line strip is a little different here. So here, you take 4 vertices, that gives you 2 lines. Here, you take 3 vertices to give you 2 lines. It's more efficient, but all the lines now have to be connected. That's the trade-off between strip and list. And it's the same idea with triangle list. With a triangle list, you have 0, 1, and 2. That gives you a triangle. 3, 4, and 5. That gives you another triangle. Whereas with a strip, they've all got to be connected, but now you're more efficient in your use of vertices. So you got to tell Direct3D which of these guys you want to use. And what we've got here is a big old list of triangles. It has exactly 1 triangle, 3 vertices. So we want to set this bad boy to a triangle list configuration. So we go p context, and this is going to be the input assembler, because that's the thing that assembles our input into primitives, like triangles or lines. And we want to set primitive topology, and it takes D3D11 primitive topology. And that's just a big old enum, so if I double colon that bad boy, now I can get a list of all the options. And there's lots in here. Many of them have to do with geometry shaders or tessellation. So we don't care about them. We're looking for Direct3D11, primitive topology triangle list. And there you go. So I mean, if we want to make that a little shorter, we could exclude this, because it's not an enum class, it's just a standard enum, so it leaks into the global namespace. But anyways, there you go. We've set our primitive topology. Now, if we run this, we should be 1 error down. And there you go. We're down to a single error. Now, this one is a doozy. It's going to require a little bit of work from us. So it's telling us that it expects input data, but none is bound. What does that actually mean, though? Because we're binding input data, right? That's our vertices. That's the input data. So why is it complaining that there's no input data? Well, here's the thing. Direct3D, we're just binding it a big buffer of bytes, basically. I mean, it has some information. It knows the size of each element in a buffer. It knows the size of the entire buffer, what the buffer is being used for. But it doesn't have any information about the actual layout of each vertex. How many elements are in a vertex? What does each element mean? What is it for? What does it do? So we got to tell Direct3D exactly what the stuff in our vertices, what does it mean, and how does it relate to the vertex shader. And the way you do this is you create an input layout object, and then you bind that to the pipeline. So we need a com pointer for an input layout, and then we need a descriptor that describes the input layout. And that's what we're going to use to construct it. So the descriptor is actually an array of descriptors. So every element in our vertex is going to have one element in this descriptor array. Now our vertex has only a single element. You might be saying, Chili, there's two floats in here. That's two elements. But in terms of the pixel shader, this just looks like one thing, one single vector position. So these two are lumped together as a single element. So that means that we're going to have one element in this array of descriptors. All right, so we should probably look up what's the format of this descriptor structure. And here we go. We've got semantic name, semantic index, format of the element. This is the most important part. Input slot, byte offset. That's the offset of that element in the entire structure from the beginning of the structure. And then we have input slot class and instant data step rate. Now, both of these are for instanced rendering. They're for giving a single piece of geometry into the pipeline and having it create multiple copies of it, draw multiple copies in a single call. So we're not going to do that for a while. So these last two guys, not very important. Also, input slot, we're always going to bind to slot 0. So this guy, not very important. So mainly, we're looking at these three guys and then this guy here. So let's take a look at what I've gotten here. So first thing is the semantic name. This has to match up with some input in your vertex shader. So here we've labeled it position. So we've got to label this one position. Now the second one is the index of the semantic. So in your vertex shader, you could have multiple semantics, position 0, and then position 1, and then position 2. And if you do that, then what you'd have to do is you would, put 0, 1, 2 in these slots here. But since we're not using indices, it just defaults to 0. So you don't have to put anything there. Here is the most important part about this descriptor, because it tells us what data is in this element. So we can see right here, it's telling us it's a floating point data, and it has two elements, two 32-bit elements, right? R and G. Now, the R and G part, ignore that. That is just some stuff that Microsoft put in there to basically just weed out the weak. It's a distraction because it makes you think that this has to do with color, but it doesn't. It doesn't have anything to do with color. It could be used for color, but it doesn't have to be used for color. All we're saying here is that we want this element consists of two floating point values. So there's a giant list of these format values here. It's an enumeration, and you've got a whole bunch of them in here, right? You've got, 4 element floats, 4 element 16-bit floats or short floats, 3 element floats. You've got 4 8-bit values packed in, interpreted as normalized values.
Pineapple shrimp, lemon shrimp, coconut shrimp, pepper shrimp, shrimp soup, shrimp stew, shrimp salad.
There's a whole bunch of bullshit in here, and we're going to go over a lot of it in the future. But basically, all you need to know for now is this is telling us we got 2 floating point values. That's our X and Y. And that's all Direct 3D needs to know. So the next 2 things here, the slot that you're binding to, we're always going to bind to slot 0. So just keep this 0 for now. Maybe in the future, we'll look at other options. And this one here is the offset in bytes from the beginning of the structure here. So this is the first element. Obviously, the offset is going to be 0, right? That's pretty simple. Now, this last one here, it's tricky, and I'm not going to go into it because it doesn't apply yet. It's a D3D11 input classification. And there's 2 options. There's vertex data, and then there's per instance data. And we're always going to be setting it, for the time being, to per vertex data. But I suppose in sometime in the future, we'll look at instanced rendering, and then we're going to use per instance data, and we're also going to be using this last value here. But for now, just put it out of your mind. Don't worry about it. It doesn't freaking matter. The main guys we're going to look at is this guy, this guy, this guy, and maybe sometimes this guy. That's it. All right, so now we got our array of descriptors. This describes our vertex format. So now we're actually going to create our input layout object. So again, when creating objects, you're going to use your pDevice interface. We're going to call create input layout. It takes 5 inputs here. Many of them should be pretty simple. One is you're going to be your pointer to your array of descriptors. That's the thing we just made. Number of elements in that array. Here's a little interesting one. It wants the bytecode of the shader, of a vertex shader, actually. And it wants the length of that bytecode. You may be wondering, why does it want the bytecode for the shader? We're binding the shader in a different function. Why do you want that for the input layout? And the reason why it needs this is because it actually checks your descriptors against your shader to make sure that the semantics line up. So we're going to need that bytecode again here. And the last thing is, of course, your PP. That's the output parameter to fill your input layout interface pointer. So in here, we're passing the pointer to our descriptor array, the number of elements in the descriptor array. Now we want to pass it our bytecode for our vertex shader, but the problem is that the vertex shader is being created down here. So we got to move things around a little bit. So I'm going to cut that out, and I'm going to put it after we have loaded and bound our shaders. So that's going to go right in here. Now we're also going to have to change the order we load our shaders in, because we need to use the bytecode from the vertex shader, but that blob gets overwritten when we load the pixel shader. So let's load the pixel shader first, the vertex shader second, and then that bytecode will still be in the blob, and we can use it down here. So that's going to look like this. We'll create the pixel shader first, create the vertex shader second. The blob still contains the vertex shader bytecode, and we can use that to validate our input layout. And that should be it. We should all be done here. It's the moment of truth. Drum roll, please. Okay, I lied. Actually, we just created the input layout. We still got to bind that input layout to the pipeline. So, gotcha. And that's going to look something like this, right? We just call context input assembler set input layout, and we give it the pointer to the input layout. Let's try it now. And here we go. We have our beautiful white Dorito. Doesn't it look delicious? Doesn't it taste like rendering and goodness? All right, my dudes, that is going to do it for today. Now we've got a minimal pipeline all set up and working. So now that all that hard work is done, now we can just do little minor incremental changes here and there and see what happens and play with it and broaden our understanding of Direct3D 11. Now the code is very dirty, very sloppy right now. It's going to stay dirty for a while. We want to optimize our code right now for one parameter, and that is being dirt simple. In the future, we are going to make better systems, better processes, better architectures. I mean, right now, I know you don't have to tell me. I know it's slow. I know it's very slow to recreate all the resources every single time we call the draw function. But it's not an issue right now for things that we are learning, and I will be addressing this in the future, and incrementally, we will be improving our system. Those of you who have followed from beginner, you probably already know me by now. You know my modus operandi. I don't just take you straight to the answer and give you a big information dump. No, I want to take you on a journey, and that's what we're going to do. Now, for those of you watching as I'm uploading these things, you might be impatient for progress to get to the next videos. And I got two things to say to you. First off is we've set up this pipeline, like I've said, the minimal that works, and we've added a whole bunch of neat stuff for diagnostics. This is the perfect playground for you to explore on your own. You don't need to wait for me to upload the next video to learn the new things. You can already start to explore a whole bunch of stuff on your own, just changing things, seeing what happens, and hopefully also looking stuff up on Google, on MSDN. Just that experience of learning how to explore an API on your own is probably more valuable than any of the details that I'll be teaching you in these videos. Now, you've heard me throughout this video reference 3D fundamentals many times, and in future videos, it's just going to get worse. I'm going to be constantly referring back to 3D fundamentals. And if you haven't watched it, you might be annoyed. Those of you who have watched 3D fundamentals, you'll be nodding along. But those of you who haven't watched it will be like, what the fuck is this guy talking about? So if you're waiting for new videos and you haven't watched 3D fundamentals yet, I strongly recommend that you go back and watch that, because having that background knowledge under your belt is gonna make it way better when you watch these hardware 3D videos. So those are my two pieces of advice if you're waiting for new videos. Number one, explore. Number two, watch 3D fundamentals if you haven't already. And in the next video, that's what I'm going to be doing myself. I'm going to be exploring some of the different variations that we can play around with this new pipeline. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And now I will see you soon with some more Hardware 3D.